Thank you, Emery. Hello, everyone. My name is Tanush Vadhavan. I'm the process engineer, and I'm talking from Toronto, Canada, and I'll be taking you through SUMO24 and some of the new features and models we've been working on. I'm just gonna shut off my video, so it's not. All right, SUMO24. Let's begin. Before we get into the technical aspect of things, I want to okay, so this is a bit let me see. Guys, give me just 1 second here. Emery, I'm gonna pass on. Oh, I see.
It seems okay here, no?
Seems okay, but I think I have people waiting on me to let them in somehow.
Yeah.
Let people in. All right. So people are in. So this is our team. We have a lot of engineers, a lot of programmers, and having too much fun. Imri in the middle, controlling the drone. And we are in Hungary in this picture, and enjoying development, identifying new features for Sumo, new products for Dynamita, and having some good fun doing modeling. I wanted to mention some of the key aspects of Dynamita. You know, what we have in our mind when we are coming up with products or trying to support our clients. We believe in constant and rigorous improvement of modeling experience for our customers. So we are constantly working on improving the software, improving the models we have. We are trying to develop at the edge of the innovation. You know, we are doing a lot of new stuff, such as digital twin, hybrid modeling, and which is basically going to improve our industry quite a bit and will have a big impact. So we're always trying to identify new developments which we can do, which are innovative and beneficial to our field. And we are continuously working to allow integration of Sumo into workflow of our clients. We try to support our clients as much as possible. You saw in the previous slide that we are a big team. We're working, you know, a lot of our engineers and programmers are in Europe. Myself, I'm in North America. So around the clock support is available if needed. And we try to align our development cycle with our clients' needs. So we identify, okay, maybe next year our clients might want to use PFAS modeling or want to do digital twin in a certain way. And then we try to see if we can incorporate those ideas, those needs of our clients in our current development cycle. So if you have ideas, if you have models that you'll be working in a year from now, feel free to reach out to us and tell us more about it, and maybe we can include it in our development cycle, which will help you. All right. Okay. So agenda for today is we'll basically focus on the graphical user interface and some of the advanced simulation features which we have introduced, such as scenario evaluation, scenario analysis, and optimizer. And I'll talk about how these three are a little bit different and do many different simulations here. Then we'll briefly touch on the digital twin capabilities we have, and then we'll talk about the biokinetic model updates. All right, diving into the graphical user interface and advanced simulation. So first thing we'll do is we'll open up Sumo and we'll start building a plant right away. Then we'll evaluate the impact of temperature on effluent ammonia. And we'll basically do this by setting up different scenarios, a single scenario and a multiple scenario, and then do those simulations simultaneously. And you can see the results in Sumo itself. And then we will perform a scenario analysis or a parameter analysis. All right. I have SUMO24 open on my side. I hope everybody can see it. Let me just get a few more people in. The first thing I want to point to people is regarding the Wiki page. So if you open Sumo, you'll see that in the documentation tab, we have a Wiki page. If you click on this Wiki page, it opens up a website. We try to keep this website as current as possible. If you're still using Sumo22, the documentation for Sumo22 will be available as a PDF right here. However, if you want to know what's new in Sumo24, that information is available. If you want to look at in detail about the advanced simulation features which we have included, that's right here. But all the information regarding the new models, which I'll be touching on, is provided as part of this document. So I highly recommend looking at this document when you have time. Okay, going back to the simulator, we have introduced this new tab at the bottom where we just used to have one tab with all of our examples. So we have created different tabs which have dedicated examples. You can see, and then in the advanced mode, we have some of the examples which talk about the advanced features. All right, so let's go to the configure tab. In the configure tab, we'll start building a plant and we'll build an MLE configuration to begin with. So I'll go to the flow elements. I'll drag and drop an influent to the drawing board. And then I'll grab 2 CSTRs. I'll go to the separators and drag a primary clarifier, place it right after the influent, grab a secondary clarifier, an effluent port, and get a side flow divider so that I can recycle the nitrified mixed liquor from this tank. I'll basically connect the CSTRs right here. I'll recycle the RAS back to the head of the CSTR, but I need a divider to waste my sludge. So I'm going to bring in a divider, turn it around, and then connect that divider to the input. I'll use a side flow combiner, right click, and do a mirror up down. And then essentially let my primary effluent go into I'll connect the influent to the primary input port, and then a sludge line right here. What I'm missing is a divider which connects the recycled flow. So I'm going to just disconnect this pipe, right click, disconnect. And then I'm going to bring another side flow combiner and place that right in the middle. Okay. So we have a MLE configuration setup. I'm going to click on the first CSTR and make sure I select the calculated dissolved oxygen model option. This model option will allow me to turn the airflow to 0 as an input so that there is no DO in the anaerobic reactor. I will go over to my model tab. In the model tab, I have one-step nitrification, denitrification model selected as an input. If I scroll down, we have introduced a new option called micropollutants, where you can look at PFAS. So currently PFAS are not considered, but if I turn it on, then PFAS will be part of this influent model, and you can specify the PFAS concentration, and then you can track PFAS through the plant. Let's go over to the tool. In the tools tab, we'll create an SRT calculation. So I'll click on the sludge retention time. I'll drag the two CSTRs to the numerator, and then the wastage or the divider along with the effluent solids to the denominator of this equation. And this allows me to create a total SRT calculation. Similar to the sludge retention time, we have introduced an option to calculate the hydraulic retention time as well. So if I click on the hydraulic retention time, I can select my reactor and then specify the influent at the bottom. And this allows me to calculate the actual design HRT of the system. Let's go to the input setup. In the input, if I click on my influent, and then on the left-hand side bottom, if I click on show all, go to other influent components. At the bottom, there is information which you can provide regarding the PFAS option, which we just switched on in the model tab. So if you want to specify PFAS in the influent and look at what happens when it goes through the plant, then you can provide PFAS as an input right here. Now I'll provide volumes to my CSTRs. So the first CSTR is an anaerobic tank or an anoxic tank. I'm just gonna name it anoxic. The second is aerobic. I'm gonna rename that one. For the anoxic tank, I'm gonna choose a volume of 3,000 cubic meter. We're dealing with SI units because we have people from all around the world joining us today. Specifically for people in the US, you can go to the options, unit system, and then select US units. So I changed the volume in the anoxic tank to 3,000 cubic meter. I'm gonna go to the aeration setting and make sure there is no airflow. So that's 0. I'm gonna go to the aerobic tank and then provide a volume of 7,000 cubic meter. I can click on my SRT on top of my drawing board, and this is the SRT calculation which we just created. I'm gonna turn on the controller so that I don't have to specify the wastage, but I can provide an SRT value, let's say of 5 days, and the wastage will be calculated by the model. I can go to my side flow divider, although I can control this as well using the proportional flow divider option in the tools. For now, I'll just provide a flow rate of 72,000 cubic meter per day. Okay. Before we move on, I would like to go back to my influent. And because this exercise is about some of the new features in SUMO, I want you to look at this advanced column. This advanced column exists for all of the process units. It also exists for the model parameters. So if I go back to model parameter, I click on my key parameters, you can see there is advanced option, advanced column, where I can actually select any of these parameters. So wherever you see this option, you basically can select that as an advanced scenario. I'm going to do the same thing for the SRT as well. So I'm going to go to the SRT, select my SRT target as part of the advanced. And this, when I go to the simulate, allows me to bring the scenario, the parameters or variables which I've selected into my simulate tab. But let's prepare a table and a time chart first. So I'm going to go back to the output setup. I'm going to add a table, click on my influent, and simply drag the frequently used variable to the right. I'll do the same thing for the anoxic, but by dragging the anoxic tank to the bottom. Same thing for the aerobic and for my final effluent. I would also like to make sure my SRT is correct. So I'm going to go click on my SRT while I'm in the output tab. Other variables, click on the SRT and drag the SRT to the right. Currently, it's 30 days because I haven't run the simulation yet. All right. So let's go to the simulate tab. And I'm going to do a steady state start. Now, before I run a simulation, you can see that if you're a SUMO24 user, this looks a bit different than what it was in SUMO24. And I want to go back to my slide a little bit. And help you see the difference between the buttons which we have introduced. We have consolidated the two tabs which we had. Previously, we had a steady state tab where you would do calculate steady state, and then we would have a dynamic tab where you would either do a dynamic run or do a steady state start, which is a steady state run plus the dynamic run. We have consolidated the two tabs into these dials. So this red button is the dynamic run start. The circular button is the steady state. And the combination of two, which looks something like this, is the steady state start. The other options remain pretty much the same. So for example, if you notice, this is our fast solver setting. This is our accurate solver setting. You can still reset. You can still continue the simulation if you extend the stop time. Okay, so let's go back and let's create a time chart as well. I'm going to go to the output. I'm going to add a time chart for effluent nitrogen concentration. So I'm going to click on my effluent, nitrogen components. I'm going to get ammonia and nitrate and nitrite. I'm going to rename this N in effluent. I'm going to also create a time chart for mixed liquor. So I'm going to click on my aerobic tank. From the left-hand side, I'm going to go and grab my TSS. MLSS. I'm going to rename the time chart. All right. So let's go to the simulate tab. And I'm going to press the steady state start button. Okay. So it did a steady state run plus 1 day of dynamic run using the parameters which we have specified here. We just want to make sure our SRT was 5 days so we can go back to the frequently used table. Okay, it's 5 days. We can look at our mixed liquor concentration, close to 1200 milligram per liter. All right. And our temperature is 20 degrees Celsius. Now, let's do a scenario evaluation where we create another scenario and then we change the temperature from 20 degrees Celsius to, let's say, 15 degrees Celsius. But before we do the simulation, we have to make sure that the boxes next to these tabs are checked. So right now, the only one which is checked is this default scenario. So if I uncheck this for a second and I try to press any of the buttons, it says select scenario. So I'm going to say, okay, I'm going to do scenario number 1. So I'm going to check scenario number 1, redo the simulation using steady state start. But before I press, let's see what the ammonia concentration is. Ammonia concentration is 1.2 in the effluent. So when I do a steady state start, okay, it jumps up to close to 4 milligram nitrogen per liter. Now, in SUMO, what we have introduced is you can run multiple scenarios at the same time and review the results on the same time chart. If I select this default scenario and scenario 1 and create, let's say, another scenario which I want to simulate for temperature at 25 degrees Celsius and press the steady state start, you can see that I have all the 3 check boxes checked. All right. What you see on your screen is that SUMO did all the 3 scenarios in parallel and projected those results on a time chart. So if I bring my mouse to the first one at the bottom, this is scenario 2. You can see that the effluent is 0.6 milligram nitrogen per liter. If I go to this other line, which is 1.2 milligram per liter, that's the default scenario. And our default scenario was 20 degrees Celsius. And if I go to the other blue line, that's where the temperature is 15 degrees. So you are able to see all these 3 results for these 3 different scenarios on the same time chart. We can do the same thing for the mixed liquor. Obviously, the mixed liquor changes has an impact of temperature. If we go to frequently used variables, okay, the table obviously shows one value for one of the scenarios. So that's scenario 2. But you can right click, go to select run, and then select scenario number 1. And then the values which you would see would be for that particular scenario. If I right click and go to default scenario, then obviously the values you see are for default scenario. Now, once we are done with this evaluation, we can simply create a report. So if I create this report, name it MLE, all the information regarding the scenario runs will be part of this report. If I go to the modified parameters, you would have the information regarding the 3 scenarios which we set up. You have the values which we changed. And if I go to the frequently used table, you will have outputs for all these scenarios. Even for a time chart, you can see that we would have that information available for all the scenarios. So it allows you to do post analysis of all your scenarios which you have run quite easily from one Excel file. All right, I'm going to close this. I'm going to go back to SUMO. And now I'm going to show another advanced feature of SUMO. So right now you can see we are in the Simulate tab. The Simulate tab has been divided into what we used to call Simulate and an Advanced tab. So if I click on the Advanced, you can see that the tabs look a bit different. And in each tab, there is this drop-down menu which says either you should analyze or you should optimize. And before we get into optimize, let's do an analyze. What does analyze do? And how is it different from a scenario evaluation, which we just did? So in scenario evaluation, we created multiple tabs and we set the values to whatever we wanted. So it's a fixed value. However, when we are dealing with the analyze, you can think of it as a sensitivity analysis, as a parameter analysis. So let's see what happens if I select temperature as a variable for doing a sensitivity analysis in this simulation. I get an option of defining what my range is. So my range is from 10 degrees Celsius to 30 degrees Celsius. The steps which you see are the simulation intervals. So I want to do 5 simulations between 10 degrees Celsius and 30 degrees Celsius. And this time, I'm going to do a steady state. So I'm going to click on steady state, but before I do, I would change to a time chart, because what I want to see is what is the impact of this temperature range on the ammonia concentration. And if I do a steady state run, you would see that SUMO automatically converts a time chart into an XY chart. And you can see the impact of temperature on the ammonia concentration. So the ammonia concentration at 10 degrees Celsius obviously reaches high. There is not enough, the cold temperature washes out nitrifiers, and then the ammonia drops to 4 milligram nitrogen per liter, close to 15 degrees Celsius, and then obviously you get complete nitrification. Now, this is very interesting because this allows you to analyze the impact of temperature on the variables. But the XY chart only shows up when you do a steady state. If you do a steady state start or a dynamic run, then the XY chart won't be of any relevance. But what SUMO will do instead is plot all those results for 5 simulations on the same time chart. And now you have an option of creating a report and doing further analysis, but all of that data will be part of the report. And similar to how we were able to look at each table for each scenario run, SUMO will allow you for every graph to look at a different scenario and the results. So for example, right now we are looking at a table where the temperature was set to 30 degrees Celsius. If I right click, go to select run, you can see that I have 5 options here. So I can go and see what is my ammonia concentration in this table when the temperature is set to 10 degrees Celsius. Okay, that's what that is. Nice. All right. So let's reverse this a little bit, because a lot of times we want to look at what is the minimum SRT to operate a plant at, let's say, 10 degrees Celsius, 10 degrees Celsius of temperature. So instead of selecting temperature, let me select SRT for a change. And I'm going to vary the SRT from, let's say, 3 days of SRT to, let's say, 15 days of SRT. And I want SUMO to do 10 simulations in between. And I want to look at that beautiful graph of the XY chart graph. So I'm going to select just one parameter and I'm going to do a steady state run. Okay. So I'm looking at 30 degrees Celsius, obviously. So I'm going to pause the simulation, or the simulation is already complete, actually. Maybe one more. All right. So I'm going to change the temperature here, not to 30 degrees, to 10 degrees Celsius and redo this run. All right. So that's what I wanted to see. up to 6 days or 5 days, 5.5 days, no ammonia removal. You start to see ammonia removal a little bit as the SRT goes up. And then obviously, after 8 days of SRT at 10 degrees Celsius for this plant, you start to see nitrification happening. And then you don't even have to choose one or the other. You can actually do multiple scenario evaluation analysis as well. So by selecting these both, you can multiply the number of simulations you're doing, and then all of those simulations will show up as part of your simulation page. Now we look at that in a different simulation, different example. So I'm going to close this example for a second. Maybe I can save it to my computer called MLE. That's it. Okay. So next simulation, which we are going to look at, is the state point analysis. Now, state point analysis is a convenient way to visualize or to determine operating condition of a clarifier. This point, which is the operational point of the clarifier, is the intersection between the overflow rate and the underflow rate. So now let's look at this graph or make this graph in SUMO while doing some scenario evaluation. We'll use the hydraulic SRT example, and we'll create 3 different scenarios and run 3 days of steady state. We'll look at a scenario where both the solids handling criteria are observed. Scenario 2 will be where the solids handling criteria 1 fail. There is not enough underflow to remove the solids from the clarifier. And the scenario 3 will be SHC2 failure, which is the solids handling criteria 2 failure. There is too much solids load in the clarifier. Now we can do all these 3 simulations simultaneously, as you saw, as in a previous example. But we look at the SPA, or the state point analysis graph. For that, I'll go back to SUMO. I'm going to open the hydraulic SRT example. And in the Configure tab, I will select the clarifier. When you click on the clarifier, on the left-hand side in the Configure tab, you would notice that we have few new different options, such as high efficiency clarifier. But for now, I'm going to select the layered flux model, because the layered flux model is where the state point analysis can be performed. I'll directly go over to the input. In the input, for me to do a scenario evaluation for the state point analysis, I would click on my clarifier and select the underflow of the sludge as part of the advanced option here. I'm going to do the same thing for the waste stage as well. So I'm going to click on this waste pump and check this advanced button. Now let's go over to the output setup. In the output setup, you'll notice at the bottom, we have the state point analysis graph. When you click on it, you can drag and drop any clarifier, any layered flux clarifier to the chart. And this will allow you to do a state point analysis. I would also create a time chart for the sludge blanket. So double click. Rename it, go to the operational. And from the operational, I'm going to get the sludge blanket height. I can also create a bar chart to look at the TSS concentration profile in the clarifier. And rename it to solids in the clarifier. Now, let's go to the Simulate tab. In the Simulate tab, I have a default scenario. I'm going to create another scenario. Make sure I check this button because I want to do all three simulations at the same time. I'm going to rename this to SHC1. Check. Make sure it's checked. SHC2. And I'm going to reduce the sludge flow to 6,000 cubic meter per day in the underflow, and for wastage in SHC2, I'm going to change the pumped flow to 400 cubic meter per day. So I'm going to waste less in SHC2 and then have a lower underflow in HSC1. Now, the key is you need a layered flux model to be able to create an SPA, state point analysis curve. You need to click on the state point analysis graph in the output tab. And then you need to drag this this clarifier to the state point analysis graph. And once you do that, you're good to go. So I'm going to go to my simulate and simply press steady state. I'm going to do a 3-day run, like I said. So I'm going to change the stop time to 3 days and then press steady state start. So using the settling curve, this is the green line. Then we have the overflow as the red line. The underflow is the blue line, and the intersection is the state point analysis. And you can see that Sumo keeps track of the simulation it's doing. So it's 1 out of 3 simulation, then it's 2 out of 3 simulation. And hopefully soon it'll be the 3 out of 3 simulation. Okay. One more to go. And all these scenario evaluations and all these sensitivity analysis which we looked at happens from the previous state of simulation. So they all are evaluated based on starting from the same time point. Okay, so this is where obviously we won't want to be. And now if I go and press on the report and save this report, you should have information regarding the SPA in this time chart as well. You can look at the sludge blanket for all the 3 scenarios and then look at solids in the clarifier for all the 3 cases as well. All right. So I'm going to go back and move on to our next exciting feature, which is the optimizer. So in the optimizer, you can use this feature to do a design. You can use this feature to fractionate your influent, and then you can use this feature to identify kinetic parameters if you have a data set and you want to calibrate it. So we'll start with the first example. So the first example is we use an MLE configuration and then we convert it into an A2O plant. And we want Sumo to tell us what is the volume and what is the wastage so that the mixed liquor target is met and the effluent quality is met. So I'm going to go back to Sumo and I'm going to open the MLE configuration from my nutrient removal tab in the examples. I'm going to press no. All right. So I'm going to use this example. I'm going to add a tank. right before the internal recycle. Right click, disconnect. I'll bring a CSTR. I'm going to right click and rename it to anaerobic. I'll select a calculated DO reactor. Next, I'll go over to the tools. In the tools, I'll go to total SRT and update my SRT calculation by adding an anaerobic tank. I'll go over to the input. In the input, I'll click on my anaerobic tank because that's what I want to design. And what do I want to design? I want SUMO to tell me what the volume is so that I can meet my effluent requirement of 0.3 milligram OP per liter. So I'm gonna select the volume for advanced. What else do I want to choose? I want to choose my wastage because when the volume is being optimized, obviously my mixed liquor keeps changing. So I want to make sure I have a target for my mixed liquor. So I'm gonna go to my VAS pump, click on the advanced button, and both volume and my VAS are now part of the simulation. So I'll go to my output. I want to make a time chart for PAOs and GAOs. So I'm going to make a time chart here, call it PAO and GAO. So I can keep track of them during the simulation. So I'm going to click on the anaerobic tank, go to the active biomass and drag phosphorus accumulating and glycogen accumulating organism. Next, I'll go to the simulate tab and then go to the advanced. All right, this is where the fun begins. So I go over to my optimize option on the left from the drop down. And you can see that a new table appears. And in this table, we have to define a variable. We have to provide a target for that variable. And then there are other important things as well, such as units of those variables and values which are automatically populated. There is weight. Sometimes one variable is more important to meet the target for. So you can do that. And then you can choose the error function which you want to use for your simulation. All right. So what do we want to optimize, or what is our target? Our target is to have an effluent orthophosphate. So I'm going to go to a time chart. Now you don't have to necessarily go to a time chart. You can actually go back to the output and drag the orthophosphate in the effluent to that table, which you see. But right now I'm going to show you two ways. The first way is to go on a time chart if it already exists. Right click on the parameter name, like I did, and click on variable to optimize. So when you click this, you'll see this blink. That means that variable is now part of this table. Now let's go to the output and add mixed liquor. So I'm going to go to the aerobic reactor. I'm going to drag the TSS right here. Okay. So you can see there are two ways of adding variables to the table. Now, let's go back to the simulate, advanced, and we want to optimize both the volume and the wastage. But we need to set appropriate ranges, because if you provide a very big range, SUMO is going to do a lot of simulation. It's going to take a lot of time. So I'm going to simplify it by giving it a narrower range of 1,000 to 2,000 cubic meters. So that's where it should identify the volume. I'm going to give it a better range for waste as well. So from 200 to 400. All right. Now, what else do I need to do? I need to provide my target. So I'm going to double click and say my target should be 0.3. Double click. My target should be 3,000 mixed liquor. The units are automatically populated. The weights can be provided. I'll talk about that in a minute. And then you can right click on the function and choose different type of error options you want to choose. So right now I'm using relative root mean square error. to minimize and meet the target, minimize the error, meet the target, and identify volume and wastage. All right, I'm gonna go and click steady state. Now Sumo will start doing number of simulations. You can see it's at simulation number 2, 3, and it's working through its way to identify what is the best volume and the wastage so that this criteria is met. Now, while the simulation is running, it could take up to a minute. We can provide additional weightage. So if the variables you have chosen to meet the target, so the targets which you have chosen are not complementary, sometimes you want to provide weightage for something which is more important. So you should think of this as providing more importance to a certain variable. So if I was to choose an absolute root mean error, maybe I want to provide a higher weightage to my orthophosphate because it's more important for me to meet my orthophosphate target is than to meet my mixed liquor concentration. Well, I guess it didn't work out as I expected it to be because I forgot to turn off the aeration in my anaerobic reactor. So I'm going to go back, change my airflow to 0, and do the steady state again. And hopefully this time it's going to be able to meet that target. I was sure I was forgetting something. Okay, you can see that it's getting closer and closer to our target. And obviously we can stop simulation at any time, but we will let this one reach the target set point. Yep, quite close. While the simulation is running, I'm going to go back and show you, re-emphasize that you can always go to the Wiki page. In the Wiki page, you can go to the advanced simulation. And you can go through step by step how to set things up and how to run the scenario evaluations or scenario analysis. We can go and see what's happening to PAOs and GAOs. You can see that it's dancing around a bit, trying to figure out what is the value where they should be. Okay, I think that's close enough. Getting very close. So we don't have to get precisely close to that. Okay, so the simulation is done. And the answer we got was this is the volume of 1497 cubic meter and 332. Yes, as engineers, we know that we don't have to get precisely the exact same number as a target is. But even then, I let it go. Now, what do I do with it next? So once we have identified the volume, we can use the same volume and the wastage to do further evaluation. For example, okay, will this give me the same amount of orthophosphate when I change the temperature? I can go back to my input, click on my influent, select my temperature, come back to simulate, and instead of doing optimize, I can do an analyze. I can uncheck the volume and my wastage. And you can see that Sumo will keep this volume and this wastage, which the model identified. And I'm going to click on my temperature, and I'm going to do 5 simulations between 10 degrees Celsius and 30 degrees Celsius at steady state by clicking on this button. And I will look at the impact on PAOs and GAOs. All right. So you can see the impact, how PAOs are going down with temperature as the high temperature is reached and GAOs are taking over. I can look at the impact of this at steady state on my orthophosphate as well. So as the temperature is changing, remember, when we did steady state with the analyze of one variable, it allows you to change a time chart into an XY chart. And now you can do more simulations if you like using the same values. All right. I'm going to close this simulation and I'm going to go over to the next one. So the next simulation which I have prepared is to fractionate the influent using an optimizer mimicking the influent tool. And then I'm going to run a dynamic data to confirm the fractionation. So this will be probably my last example, and I won't get into the example number 3 given the time we have. And then we'll talk about digital twins a little bit. Okay, so I'm going to go back to Sumo. I'm going to click on Configure tab, maybe open a new file. I'll open a new project. Configure. I'm going to drag and drop the influent. I'm going to go to my input and open up the influent tool. Now, the main purpose behind using the influent tool is to provide the data you collect from your lab and then go over to the check fractions and be able to identify what your TSS is, what your VSS is, and BOD is by estimating how these fractions are changing. And we'll set up this exact example for the optimizer. So I have a plant data from a plant, and I'm going to bring that over to Sumo. So I'm going to copy the total COD, TKN, and total phosphorus like we would in the influent tool. Then I would need, okay, how much, what is the VSS to TSS ratio, which is again data set from the plant. I'm going to go to my influent fraction and say, okay, my VSS to TSS is 92%. My filtered COD and filtered flocculated COD, again, is data from the plant. So I'm going to say 48.5% and 38.6%. And the other two remaining is the ammonia to TKN and orthophosphate to TP, which is 74 and 72%. So exactly how we would fractionate using an influent tool, I would highlight and select some of the important parameters. So which one were they? So let's go back to the tool. In the tool, you can see we have particulate and biodegradable organics, fraction of OHO. I'm going to skip the endogenous decay product because it's a small fraction. Then the colloidal and biodegradable portion, the nitrogen and phosphorus content. Okay, so I'm going to go back and select these 7 to be part of my fractionation scheme. I can also go to the model parameter which is the COD to VSS ratio, and select that as part of the advanced as well. Now, coming back to the Simulate tab, we would have to go to the advanced option. From the drop-down menu, select Optimize. And what are we optimizing? In the Influent tool, we saw we want to optimize for BOD, TSS, and VSS. So we'll do the exact same thing. I'm going to go to the output setup, click on the Influent. From the frequently used variable, I'm going to get TSS, VSS, and BOD. And I'm going to provide my target. So if I go and look at my data set, my target for BOD is 236, 169, and 155. So I'm going to type in 236, 169, and 155. I'm going to go back to the simulate in the advanced. When I have optimize selected, I'm going to select all these parameters which I want to optimize. Or identify. One thing we have to make sure is that the range which we specify should make sense. So I'm going to limit this to 2 and 1.6. The COD to VSS ratio of particulate biodegradable substrate. And I'm also going to limit the phosphorus fraction of the readily biodegradable substrate from 1.5 to just 0.5. Now, once I've provided these ranges, I'm going to press steady state. And SUMO will work through by adjusting these fractions to identify the fraction or estimating the fractions so it matches the target. I'm going to pause the simulation. I wanted my BOD to be 236. So let's see if I can. Okay, 236, 169, and 155. And press start again. Okay, so you can see that SUMO identified or estimated the fractions on the left. It's going a little bit. Okay, it's done. So it identified the fractions which work to achieve these targets. Now, we also want to verify that these average values which we have just identified also work for a dynamic condition. So by going to the output, creating a time chart for the influent TSS and BOD data from the plant, I would copy this data from this Excel file, TSS and BOD, go back to SUMO, right-click on the header and import that data by pasting and pressing OK. So that's 365 days of data, which we'll simulate. I'll go back to simulate. I'll make sure that I'm no longer in the advanced tab, but in the simulate tab. And I'm going to do 365 days of dynamic simulation. But I need to plot my TSS and BOD as well. So I'm going to go to the output and I'm going to get the TSS and BOD. For the influent, go back to simulate and press start. So eyeballing it, you can see that the TSS and BOD are quite well reproduced using the estimated fractions. Now I can go a little further and add a dynamic influent on top of this to see that if it reproduces the BOD and TSS. So I'm going to copy the dynamic data, go back to SUMO, go to the input, dynamic, and paste the table. And now if I redo the simulation of 365 days, you can see that it's a better fit based on the fractions we have just identified. So this would be another application for the optimizer, which allows you to fractionate on the fly using these advanced features. All right. I'm not going to get into our third example, but basically you can use the optimizer feature to identify for parameters using dynamic data set as well. And we'll create a short video and upload it to YouTube for this example. So if I have to summarize the difference between scenario evaluation, scenario analysis, and optimizer, in general, the simulate tab, which in SUMO24 and now even now we have, allows you to change values from the input tab and then individually run simulation. However, if you select the advanced check button next to any parameter or variable, then you can create a scenario evaluation where you can do single or multiple scenario tabs and run them individually or all of them at the same time. You can do a scenario analysis where you can look at the sensitivity and you can look at the parameter analysis or do a sensitivity analysis based on a parameter and decide a range of values where you want to do the simulation and provide the number of intervals. And all of them can be executed at the same time. And for the optimizer, you decide a target value, provide a value, and then the variables to optimize, and then you run the optimizer to achieve that target. So in summary, what can we do with SUMO24? So if you ask, can you run multiple scenarios in parallel? Yes. Can we run sensitivity analysis from inside the graphical user interface? Yes, sure. Can we auto-tune controllers to match a data set? Yes, we can. There is an example for it in SUMO under the advanced tab on the main page. Can we use SUMO optimizer for design? Yes, of course, why not? Can we use it to minimize aeration demand and maximize energy production? Can you set up an optimizer for that? Of course we can. And there is an example for both of those as part of the examples tab in SUMO's homepage. And finally, can we identify kinetic parameters for batch test? Yes, we can. All right, let's talk about digital twins a little bit. So SUMO which is a digital twin toolkit, allows us to create two different applications. One is the digital twin application, which is essentially an online representation that is connected to a real system to gather, store, and simulate live performance. While the other application of this toolkit is to be able to create applications that automate our modeling tasks. So some of the key points about the capabilities of SUMO and the digital twin toolkit are that SUMO can receive information or data and can send out information and data. It can receive information from an OPC server, SCADA, other databases, or other SUMO files as well. So that means you can run SUMO files consecutively. You can run it in series or in parallel, however you want to set it up. And SUMO can send data out to, again, back to OPC, SCADA, database, other SUMO files. How do you create this communication channel? You can use Python or C++. So write a script and it'll allow you to send data from SUMO and into SUMO. It could be a web application, it could be a cloud application, and it could be a local server. Doesn't matter where the application is. And you can create your own user interface if you want. And in the background, you could have it running. So one of the examples is right here. So in this slide, what I have is, I'm showing a simulation done in the interface of dynamic influent of the ammonia in this MLE configuration. If I click on this button, so this is a simple Microsoft PowerPoint-based interface, let's say. If I click on this button, it will ask me, do I want to run this simulation using Python? I say, okay. And then the simulation is being run in Python, and then it spits out this graph. And this graph is exactly the same graph as what you see in the PowerPoint. So this is a simple application of creating different interfaces or different applications using Python. So how does it work? You create a Python script, you interact with the SUMO scheduler, which is inside SUMO, and then you are able to run multiple simulations using the interface. And how to set this up is install the SUMO digital twin from the website, install Python, set up the Python pathway for the environmental variable following the Wiki page. So another new aspect of digital twin which we have introduced in SUMO is to simplify how to set it up. So in this configuration, we identify these are the inputs which need to enter the model from the SCADA system. So the dosage, the flow rate, COD, BOD, tank volumes, and so on. And then SUMO will give you the mixed liquor concentration, effluent COD, BOD. It might tell you a little more about the analytics which can be used, such as denitrification rate, the intrinsic data set of the model or predictions by the model, how much active fraction you have. But then, where can users struggle in setting up a digital twin? It's essentially identifying which data goes where in the model. And we have simplified this by introducing a JSON exporter. So JSON is a JavaScript object notation, and we have created an extractor. If you create a configuration in SUMO, by click of a button, you can create a JSON file. And this JSON file will contain all the information regarding all the parameters and variables which are part of that configuration. So for example, right here you can see a full symbol for dissolve oxygen set point in the CSTR. So this full symbol can be used by you to develop application to send data about the DO set point into SUMO, run SUMO, and then get information out. So all of that process unit names, symbols, the variable names and variable symbols are available in this JSON file. And processing this JSON file and SUMO24 through Python can allow you to create digital twin or other modeling applications. Here is an example of how we have used it for HRSD, for one of their facilities, which is the Nansemond digital twin, a Nansemond facility. So in our digital twin application, we get the data from the OPC server, we clean it using some algorithm, using Python. That data is sent to a SUMO interface where we are doing real-time simulation. This plant or this model file is auto-calibrated and sensitivity analysis done on a weekly basis to identify the correct SRT and wastage. And then from this model, we identify the mixed liquor composition. The mixed liquor composition from this full plant model is then sent over to this mini model, which is also receiving information about the ammonia forecast which is again developed using a Python script. And this has been done by HRSD themselves. So they have a Python script which predicts what the ammonia should be 2 hours from now. And that information, along with the mixed liquor information from this full plant, allows us to do optimization and identifying what the dissolved oxygen set point should be for next 2 hours and how the plant should operate. And now that information is saved in the SCADA system or the OPC system and is accessible if they want to use that information to operate the plant as well. And I believe this information actually goes back to the OPC to change the actual dissolved oxygen set point in the plant. Now, along with this, we have dozen more use cases of simulator. One of the references which I want to mention is the recent WRF report by Bruce Johnson on development of hybrid digital twins for predictive nutrient control. And it contains a lot of good examples of how digital twins should be implemented for various facilities. All right. I think we have a few more minutes and we can talk about some of the model updates which we have achieved in SUMO24. The first one we want to talk about is the particulate biodegradable organics and the hydrolysis rate. In SUMO22, the previous structure was that the particulate biodegradable organic from the influent gets hydrolyzed to form soluble biodegradable organics. Then eventually it gets oxidized by heterotrophs. And when the heterotrophs decay, part of it becomes XB. So previously we did not distinguish between the XB which is coming in from the influent and the XB which is coming in, is generated in the process. While now what we have is, we have XP which converts to SP, and the OHO, when they decay, they don't form XB, which is biodegradable particulate, representing the influent, but rather XBE, which is the biodegradable particulate generated from this endogenous process. And now this XBE is further hydrolyzed to SB at a much slower rate. So we have two different rates and two different particulate biodegradable substrates, one representing the influent and the other representing what's produced by the biomass during decay. And what does this allow us to do? So it allows us to distinguish between the two types of XBs, which are part of the wastewater, which is one in the influent and the other generated by the biomass, because XB in itself is quite complex organic molecule, and it allows us to simulate RAS, fermentation, side stream biopy, and anaerobic digestion more accurately, specifically if you're dealing with only primary sludge or if you're dealing with only waste activated sludge, anaerobic digestion, or in combination of two. The next update we have done is regarding the PdN, or the partial denitrification model has been introduced. Recently, there has been a paradigm shift in how we do nutrient removal, specifically focusing on NMOX. We used to look at NOB out selection or nitrite oxidizing bacteria out selection as a viable pathway, where we would convert ammonia to nitrite, and then nitrite and ammonia would be used by NMOX and converted into nitrogen gas.
With the partial denitrification pathway, we let the complete nitrification go forward. So we don't necessarily wait for just nitrite in the a complete nitrification cycle. We don't do partial nitrification. We let it go complete, and then we add a little bit of COD to form nitrite. And this nitrite, along with ammonia, is then available for NMOX for growth and removal. So we basically are preventing the nitrite to nitrogen gas through a heterotropic pathway. So nitrite reduction through an heterotropic pathway is prevented. Now, this only happens in the model and observed in experimentally tested in labs with methanol and volatile fatty acids and maybe glycerol as well. So we have implemented this model, which allows us to simulate nitrite buildup during a denitrification pathway when we dose methanol and volatile fatty acids, while not with SB. SB is the readily biodegradable organics, which comes with the influent or is a product of hydrolysis. It allows us, if the electron donor, which is the methanol or volatile fatty acids, are a lot more than the electron acceptor, in this case nitrite, then the PdN pathway does not work. So if you have too much electron donors in the environment and too little nitrite, then obviously nitrite buildup doesn't happen. Nitrite is also denitrified. The residual nitrate inhibits nitrite reduction. So nitrite buildup can be simulated for PdN or PdN-A performance. And this batch test shows an example of how the model works. So the red dots are essentially nitrate. The green line represents nitrate in the model using VFA addition. The blue dots is nitrite buildup during a batch test when VFA was dosed. And then the blue line is what the model now predicts. So if we were to increase the VFA concentration or dosage in this batch test, then the model will not simulate nitrite buildup. But this nitrite buildup is essential for PdN-A to occur. And the new model is able to simulate that process. And finally, I want to touch a little bit on the greenhouse gas model, which is the SUMO4N model. In the greenhouse gas model, it's a 4-step nitrification denitrification model where the ammonia is converted to ammonium hydroxide. And then we have nitric oxide, which is internally generated as a state variable, which converts to nitrite. The NOVs will convert nitrite to nitrate. And then ordinary heterotrophs or OHOs will play a role in denitrification from nitrate to nitrite. And then again, we have nitric oxide generated internally by heterotrophs before nitrous oxide is released. So there is a nitrifying pathway by nitrifiers, and then there is a denitrifying pathway, which allows for nitrous oxide emission. And recently, we have introduced abiotic oxidation as well as part of the greenhouse gas model. Some of the model references are available on our Wiki page, and more information about the model can be accessed from there as well. And finally, a few lines about the sludge densification add-on. So if I go back to the Wiki page for a second, if I go to home, what's new in SUMO24? So like I said, there are more information can be accessed about the new features, new process units, new tools, and then new add-ons. So the densified sludge add-on allows us to simulate densification or granulation of sludge when a cyclone is presented as part of the configuration. And I want to just talk about the difference between the biofilm model and the new add-on, which is the sludge densification add-on. So in the biofilm model, we have the MBBR, which is a one-dimensional biofilm model. The media does not leave the reactor. So you can imagine that there is a screen as part of this, each of these reactors, and the media stays in. We have another add-on called the mobile carrier add-on, in which the media is actually free to move along the whole plant. So the biofilm and the media moves freely through the plant. Again, that's a one-dimensional model as well. And now what we have introduced as an add-on is a 0D model. In a 0D model, you would set up a configuration like we just did, except choose a sludge densification model as a biokinetic model, and then add a cyclone. Now, what this cyclone allows us to do is to capture granules as they grow in the system. We have duplicated the biomass. So there is an OHO for flock, and then there is an OHO for granules. There is AOBs or ammonia oxidizing bacteria for flock, and then there is ammonia oxidizing bacteria for granules. And as the wastewater flows through the cyclone works to capture granules and lets the flock pass out and allows you to simulate the sludge densification process. And the important parameters which are involved in a 1D model is a big list of parameters such as biofilm thickness, boundary layer thickness, biofilm specific mass, media-related or carrier-related information such as surface area or fill percentage is to be provided when we are dealing with 1D. But when we are dealing with 0D model, we have to provide just two kinds of information. One is, what is the mass split between granules and flocks associated with cyclones? And then diffusion resistant factor, which we have introduced for biomasses that are associated with granules. And that allows us to simulate the sludge densification process. All right. With that, I would end this presentation, and I would ask you guys to go to the Wiki page for more information about what we have as new process units, new models, and more detailed information about the model descriptions. Thank you very much for joining us today. And if we can still leave the chat on for a couple of minutes.
Thank you, Tanush.
All right, I'll stop the recording now.